Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
So where we left off, we were talking about transformations of random variables, and we're going to, in the end, have 4 methods of doing that. I'll review the 2 that we've pretty much covered. So just to remind you, we're talking about transformations. Okay. So transformations in general means you have a random variable. I don't know why it's not showing that. Thanks for telling me. It's showing it here. Doing transformation. So in general, that might be, you can imagine a variable y which is a function of another variable x. And we're focusing on the continuous case. There's a good reason for that. If you're talking about discrete random variables, it just takes a list of values. So, you know, like for instance, let's think about geometric 1/2, which is the number of coin flips till success. If x is the number of coin flips till success, well, it's probability of half of being 1, quarter of being 2, and eighth of being 3. If you double that, then it's just probability of half of being 2, quarter of being 4, eighth of being 6. So you take the same probability mass function and move it to the new variable spot, g of x instead of x. So there's nothing to it. That's why I can go. So it's slightly more complicated when you have densities involved. And so number 1, which you could have done even before we knew much about densities, was to, I call it the CDF method. You have to, start with fx of, you have a function fx of x. That should allow you to calculate fy of y, and that should calculate, by differentiating, should allow you to calculate the density of y. Very much a one variable case. I wouldn't like anyone to try a CDF in 2 or higher dimensions because, that CDF in multivariate is the probability of the lower left quadrant or lower left octant in 3 dimensions or more. It's very complicated, and then if you transform, that would not be an octant at all. So hard to make sense of that in high dimensions. So the second was, really you could prove this using the CDF method, but it was the PDF. If you want to know what it is, it's the density function times the absolute value of G inverse prime of y. So that's kind of, I'm not really, it's a PDF method where you multiply by the appropriate thing. So that's in inverted commas. But really, seriously, if G is, let's say, differentiable. It has to be differentiable for this to really make sense. And if it's not differentiable, you might not even get a continuous variable y. In fact, if it's differentiable and constant, you also might not get a continuous y. But if g is differentiable and g, sorry, that should be not g inverse of y, g inverse prime y. You multiply by a derivative. And, well, yeah, g inverse prime of y exists. Sorry, and it's very important that it is 1 to 1. Then the density of y, you find the appropriate, now the appropriate point x is not hard to see, that it has to be g inverse of y. That's the x value that gives you y. And then you multiply by the g inverse prime of y, which is the same as dividing by g inverse prime of x. And the best way to think about it, if you have an equation y equals g of x, and you allow x and y to vary, this Leibniz notation, I still think is probably the simplest way to think about this, because it's easy. Fx of x, because x is g inverse of y, times the absolute value dx dy. And that makes even more sense, because you can, and in inverted commas, I don't like to split up the derivative, but if you do fy of y dy, that's the probability of lying in a small region around y. And correspondingly, fx of x, length of dx, that's the probability of lying in the corresponding small region around x. So that's why it is that way. But that's probably a more precise way to do it. If g is not 1 to 1, you can have multiple. That would corresponding to multiple x values giving the same y value. And then you just do the same thing, sum over so f y of y equal to f x of x. You sum, no, sorry, I have to sum over the different x values such that g of x equals y, because all of those may have different densities. So each of those you have the density at that point times the, I guess, let's say 1 over absolute g prime of that point. If you're wondering how g inverse prime of y and g prime of x are related, they're reciprocals. You would remember that from the chain rule in calculus. So if it's not 1 to 1, you have to have multiple points. And of course, so long as each of these is non-zero. So assume it's non-zero. Once again, if it is equal to 0, then maybe the density doesn't exist. So assume that is non-zero. Okay, so that's a brief recap of the PDF method. And if you really wanted to prove that, you could go via the CDF method and differentiate the appropriate point and substitute in, xi, the various roots. You might not have explicit formulas, but that can be proved using the CDF method. But that's what it is. Hopefully, most of the time, it's a one-to-one function, so you can just use the simpler form. So number 3 was use MGS, and I only managed to say the idea of this at the end of last time. And the key fact about MGS we're using is that if mx of t equals m, well, actually I'm going to, x was my original thing before transformation, so I'm going to use z and y. If mz of t is equals my of t near 0. Remember that moment generating functions don't always exist everywhere, and sometimes they exist nowhere. So it needs to be somewhere near 0, but it could only be for a short patch near 0. So if then z and y have exactly the same distribution, exactly the same, not just approximate. There's even an approximation version, which we don't do in this class. If one MGF tends to another MGF, then the distribution tends to another distribution. So actually, that's one way of proving the central limit theorem. But for the moment, we just need the equality version. If the MGFs are the same, then the distributions are the same. That's good because often you can calculate the MGF quite easily. So let's, depending on what the transformation is, of course, sometimes this won't work. So start with x being normal 0, 1. I know normally z is normal 0, 1, but let's say x is normal 0, 1 here. And we've already calculated mx of t. If anyone forgot what that is, it is, of course, expected value of e to the tx. It's the definition of the moment generating function. And we calculated it's e to the 1/2 t squared for a standard normal. So there's a baby case, which I'll call A. The baby case is one we've already done. But let's do y equals a linear transformation of x. So I'm going to make y equal to a plus bx. Okay? So that's just shift by a, scale by b. And then expected value of e to the t a plus bx. That's how I find the MGF of y. Y is a plus bx. That's expected value of, there's two factors here, e to the at plus btx, okay? And I can take the constant factor out the front. E to the at, expected value of e to the btx. And I think we even mentioned this at the time, talking about moment generating functions. The key thing that happens there is that is equal to e to the at mx, but you have to substitute in a different argument. It's not expected e to the tx, it's btx, so I've substituted in btx. So that's because of the definition of moment generating function. So that is e to the at plus 1/2 b squared t squared, because mx of bt is e to 1/2 bt squared t squared. So, and I guess if you were to define the normal that was not standardized by means of its density, you could calculate its MGF was exactly the same, and you conclude it's the same. So if you do it that way, then you conclude that y has the distribution normal with mean a, variance is b squared. Okay, so no big surprise there. Let's do something a bit harder that we haven't already calculated. Let's try now y equals x squared. Okay, so x was a standard normal, and y was not. Now we have done this by method 1, and we just want to check that what we get by method 3 is the same as 1 and 2. So to do that, we want my of t, in case it wasn't clear, this is my of t in case A. So my of t in case B is, as always, expected e to the t y, which is expected value e to the t x squared. Now this calculation I don't think we've done before, so let's do it. To find the expected value of a function that you don't know, a function of x that you don't already know the expectation of. If you're tempted to think what is the density of e to the tx squared, you're sort of missing the point, because that would be doing part 2. That would be doing method 2. You could find density of e to the tx squared, although that would be even more complicated and you'd be using part 2. So we don't want to do it that way. Instead, you just always use the fact that expected value of a function is function, integral of function, e to the tx squared times density, f at x of x. That's always what it is. And in this context, that's minus infinity to infinity. I have e to the tx squared, but there is of course e to the minus 1/2 x squared from the standard normal divided by square root of 2 pi. Okay? dx. That's what it is. So now I have to find the integral. And it's worth bearing in mind that the moment generating function doesn't always exist. And it's pretty easy to see that for sufficiently large values of t, this is going to cease to exist. I'll simplify it for you if you like. But, minus infinity e to the power. Let's put the x squared as a common factor. T minus 1/2 x squared divided by square root of 2 pi. Yeah. Remember, this is an integral over the whole real line. So what happens if t is large? Speak up if you could. t is a large number, and I'm trying to integrate this thing, just use your intuitive guess of whether, are things exponentially big or exponentially small. If you've got something that's exponentially big, and you're integrating over the whole real line, you've got a problem. Okay? Very, very infinite. So how big is too big for t? 1/2. And yeah, so bigger than 1/2, you'll have e to the positive number times x squared, and then x is over the whole real line. It's very, very, very large. Clearly, in order to have a density that, an integral that is finite, in order to have an integral that's finite, you clearly have to have something that's not getting too large towards the left end of the axis and the right end of the axis. So we certainly need t less than or equal to 1/2 for this to make sense. What would happen if t was equal to 1/2? Would it exist or not exist? Not exist. It's a constant, right? E to the 0 times x squared is 1. So you're trying to integrate 1 over root 2 pi of the whole line. It doesn't work. So you need t strictly less than 1/2 in order to have these nice exponentially small tails that you need. Okay? So this moment generating function, is defined up to everything less than t equals 1/2. And then it's one thing to say the integral exists. It's quite another thing to actually compute it. Does anyone, this is a bit of a trick, so I don't expect you to guess it, but does anyone have any ideas for what kind of a trick I could use? The reason I need a trick is because e to the x squared by itself doesn't have a closed form antiderivative. That's e to the constant times x squared can never be done with a closed form. But still, this is a whole real line, so we have some special values that will help us to calculate this. So if I don't know the exact antiderivative, I can hopefully relate it to something I do know. Are there any suggestions for? What do I know that is related to the integral of, something times x squared? Gamma is more related to integral of e to the minus x, but we'll actually get a gamma in the end. But it's just the normal itself. If you think about it carefully, this is not itself a density, but it can be massaged into being a constant times the density of a normal. So we'll have to take out a constant, and then we'll get the density of the normal. How are we going to do the massaging? Well, remember, it can be useful to remember the known formulas for densities. Clearly, the shifting is not an issue. This is still centered around the origin. It's centered around x equals 0. So I just need to remember e to the minus 1/2 x squared divided by, this is where it comes in handy to have memorized the density of a general normal variable. So it would be x minus mu squared if there were a mean, but the mean is 0. And what do I put on the denominator here? Sigma squared. And so on the one hand, this had better be sigma squared on the denominator. And then, does anyone remember the constant term? 1 over square root 2 pi times sigma. Exactly. You've got a sigma squared and the exponent of sigma here. Now, I better fix that up. Well, the first thing is I'd better find the value of sigma, and I'd also better not put in a spurious sigma that wasn't there to start with. So I have to multiply by sigma out the front. Okay, so I've made sigma on the numerator and sigma on the denominator. That is okay. And I'm also going to have to figure out the correct value of sigma squared. It's just a bit of algebra, I guess. This is 1/2 of 2t minus 1. Or in fact 1 minus 2t once you do this. So sigma squared 1 minus 2t? No, because it's on the denominator, right? I have 1/2 1 minus 2t, but that should actually be on the denominator. I get 1 minus 2t to the power minus 1. So check your algebra if you want, but that's exactly what it is. And then the whole point of doing this, in case it wasn't clear, is that this is now a density. It's the known density of normal 0 but sigma squared, where sigma has this particular value. Okay? So a density always integrates to 1 over the whole real line. So that equals sigma times 1. Okay? And just substitute in the value of sigma, which is the square root. So we could write it this way: 1 minus 2t to the power minus 1/2. I have to take the square root. Okay? And it's good to put the proviso, t less than 1/2. Okay? So this is the MGF. We actually calculated this once upon a time of gamma well, 1/2, 2. In general, it's 1 minus bt to the power minus a. The MGF, 1 minus bt to the power minus a. That is the MGF of gamma a. Okay? In case you forgot. Now, clearly, this method is not so great if you don't have a library of known MGFs in your head, or in fact, frequently you won't get something that's in the library of known results. But sometimes it can be useful, this method. So I'm not going to dwell on it anymore, except to say that quite a few things can be done by that method. And as I say, all of these are most useful for continuous. The transformations of discrete random variables are actually less frequent than you might think, because usually it's in a natural, like normally you're counting integers. If you double or triple that or do a transformation of that, it's not as natural. So really, it's most of interest for the continuous random variables that have a density. Now, that's not to say it's only useful in one dimension. Those are the ones we've done so far. So we do now want to start talking about some higher dimensional transformations. So I warn you, there's a little bit of maths or calculus in this, but not too much, and you'll be able to do some calculations by hand quite easily. But you do need to steel yourself for the fact that we will have 2 variables of input and 2 variables of output. So let me, okay, that's the new heading. Okay. By the way, it is transformation method number 4. And although it seems like it might only apply to 2 and higher dimensions, it's actually useful for 1 dimension too. I'll give you a good example of that in a moment. But this is the general, we'll talk about general smooth transformations. Smooth, for our purposes here, you can take as a synonym of differentiable, or a nice continuous derivative. Smooth, but so it means not some kind of jerky thing with piecewise, and certainly not something discrete. It has to be a smooth transformations of continuous multivariate. Okay. We already know how to do the univariate case. Random variables. Okay. And what this will actually end up being is the d greater than 1 case. This is the d greater than 1. D is a number of dimensions, analog of method 2. So method 2 gave us a special rule, which is just you multiply by a certain derivative, and that's how much the density changes by. In higher dimensions, we have to find an appropriate sort of derivative to tell us how much not the length transforms by, but how much does the area transform by in 2 dimensions. So those of you who've done a multivariate calculus course will probably, that's ringing a bell. How much does area transform by when you do a smooth transformation, and it even has a name, Jacobian. You may or may not remember that name from math. If you don't worry, then I will, I'll define it. So the Jacobian of the transformation is that scale. So let's talk about it in the 2 variable case. So we have a random variable x, y. Okay, so this is a bivariate random variable. Okay, and then we have a transformed variable. Now, I'm saying variable, but it's once again it's a point variable. It's got 2 coordinates. uv is the transformed variable equals. So just to match the notation last time, I'll write g of x, y. But this is a function of 2 real inputs and gives 2 real outputs. So in case that you don't like that, it's useful to say u1 is g1. So this is now a real valued function, g1 of x, y. And u2 equals g2 of x, y. So each of them is a function of 2 variables. Okay? And it'll turn out they can't be the same function for the following reason. There's a relation. The functions can't just squash the whole plane into a point or a line. They have to be a nice, smooth transformation that is non-degenerate. That word keeps coming up again and again. It doesn't squash two dimensions into one dimension. So, G1, well, let's just say xy maps to G1 of xy, which is the u coordinate, and G2 of xy. I'm not going to do the non-one-to-one case. You could do something about adding up, but it's horrible. So we'll just imagine it is a one-to-one and onto. So another word for that is bijective. And it also has to be differentiable. Okay, so there's going to be a lot of constraints on our function for this to work. Transformation. Transformation is a fancy word for a higher dimensional function. This transforms one plane onto another from a region D to another region. What shall I call the other region? Maybe I don't want to use D1 and D2 because that'll get confused with U1 and U2. I'll call the other region D1. So let's have a little bit of a picture of that. The picture will look as... Okay, I'll continue the picture up here. So xy is lying in this plane. There's an xy plane. And then there's going to be a uv plane. Okay? Now, of course, they're both the real plane, but I try to keep... there's no reason to confuse the x and y's with u and v, so I'll just draw them separately. And I'll have a region. The region in the xy plane I call D. Now, it doesn't matter what that region is. In general, it'll probably be something simple like a rectangle, or maybe the whole upper right corner, or it could be the whole plane. But just to show you that it's quite general, I'll have a region there, D. And then there's a corresponding region in the plane over here that gets stretched and warped onto. So, but it gets stretched and warped in a very smooth fashion. So D prime. Okay. And then what happens, I'm just going to imagine, I drew it with round edges because that's the general case, but it could be. It's not actually important that it be a rounded thing, it could be a rectangle, just so long as it's a region. Okay, so the key thing is I imagine, and this is very important when we're keeping track of areas and densities and so on, it's very easy to imagine a nice little mesh like a fly screen across this region D, quite small mesh, and then that's pretty much keeping track of regularly spaced coordinates in this plane. And if each of those, remember each point gets sent to a point. I should indicate that with just a little arrow. So the arrow is saying that the whole region is sent to G. And it doesn't wrap over, it doesn't double up. Every point in D goes to exactly one point in D prime, and vice versa. And not only that, it's differentiable. So we'll even find that we're not quite finished. There's one more condition that we'll get to in a moment, which is the same as in one dimension. I didn't want the derivative to be zero. You can have bijective functions where the derivative is zero. I want to rule out derivative zero. In higher dimensions, it turns out that you don't want the Jacobian to be zero. So I'll define the Jacobian in a moment. How do I transform this across? Well, I just draw it. So the point is, I want you to be aware this doesn't have to be a linear transformation or anything like that. The only thing it has to be is smooth. And if you're thinking about, so it could have been sort of warped a little bit. But I'm imagining each of those mesh grids, which were straight on the left, got bent a bit on the right. But they never cross one another because that would it has to be one-to-one and onto and differentiable and all that kind of thing. So, and then maybe these grid lines got a bit warped too. And so it's clear then that, first of all, when you take a little square or a little rectangle on the left, it doesn't, and I don't want any criticism about my diagram not being to scale or anything. You do have a small rectangle here, and whatever it's sent to here, in the general case, that will not be a rectangle over here. It will be kind of close to having straight edges, but it won't be close to a rectangle. So maybe a good one to illustrate that is here. So whatever that is, you can imagine zooming that in. Even if you took a tiny, tiny, tiny rectangle here, you get a tiny, tiny, tiny shape here whose sides are pretty much straight, and the opposite sides will be pretty much parallel. Why is that? It's because, okay, let me, I just want, it turns out that this will follow. I'll just say with smooth derivative. So not only the function itself, but the derivative of the function has to vary smoothly from one place to another. That actually follows in most cases. But in cases where you can write down the derivative, you can just check that the derivative is differentiable. So that means that this rectangle, it's bent at some angle over here due to the derivative, but the derivative is almost the same on the other side of the rectangle, which means that is almost parallel. So, and then the bottom leg of this rectangle is bent to the bottom part here and the top. And the bottom and top are almost exactly parallel and have almost exactly the same length. So what you have is an exact rectangle. You have an almost exact parallelogram, not necessarily a rectangle, because the angle here, if it's quite a severe warping, the angle could be way off 90 degrees. So the angle could be off 90 degrees, and also there's no guarantee the length on the output would be the same as the length on the input. It's probably not. So the length would be stretched by a certain factor in the x direction, a certain factor in the y direction, and there'd be some kind of angle between them. So that's one way of measuring the area. So then the area of a unit, let me just say a small unit rectangle. What do I mean by unit? Just one of the individual ones in this mesh, mesh on the left, in the xy plane is sent under G to a small almost parallelogram. Okay, so, and I'm even going to give this area a name, dx dy. That should sort of make sense because I'm imagining a short distance here, dx, and a short distance there, dy. Okay. This will motivate the calculus formulas that we get. And so the area dx dy of a small unit rectangle is sent to a small almost parallelogram of area, okay, in UV, right? In the UV plane of area. Now, I'm going to call the area du dv, not because it's a rectangle, but just because that's the conventional way of referring to a small unit area. Like when you're doing an integral with respect to area, you write integral du dv. Du dv equals, well, I'm just going to call it absolute value j, dx dy, and I have to give you a formula for j. Now, you can derive this from first principles, and I'll give you the basics of those principles, but then I'll just give you the formula. What is the first principle? You want to find the area of, like, if this were a 1 by 1 square, you'd want to find what area the corresponding parallelogram has. And because we're zooming in so quickly, you can assume it's linear. That's the key virtue of calculus, is zooming in so far that the transformation is essentially linear on the small scale you're talking about. So it's a linear transformation from a region here to a parallelogram, and I want to find the area of that parallelogram. And at this point I feel like probably just quoting a fact from linear algebra. You've probably seen it in the linear algebra course if you took it. Okay, so if the linear transformation I'll write it in formulas in case people don't like matrices, but we can. So U equals, and I'm just going to write the matrix with the letter A. A11 x plus A12 y. V equals a21x plus a22y. So that's a linear transformation. It takes xy plane to the uv plane. And I hear your objection that the general one is not linear, but we're pretending it is because we're zooming in so far. Sends a rectangle R to a parallelogram P, so R in the xy plane, in the uv plane. Then the area of P, of course it depends on the area of R, because bigger R will be bigger P, is exactly equal in the linear case to area of R times determinant of this, all these coefficients, A11, A12, A21, A22, and for those who don't know what the determinant of, I'll write it with A, B, C, D because it's easier. It's the on-diagonal product minus the off-diagonal product, AD minus BC. And I made one important thing to put in as an absolute value sign for the determinant. The reason is the determinant can be positive or negative. As a positive sign if it's a transformation that sort of keeps the orientation, and minus it flips. We don't care whether it keeps or flips. We want it to be positive in both cases. So we put the absolute value. So that's a fact from linear algebra. I'm kind of not really sure whether I should prove that. I think I won't prove it. You can look up in a linear algebra textbook. If you're wondering, it has to be that because it's, yeah, because of linearity. It turns out this is the only bilinear function of the two rows here, or the two columns, that is 0 when it's a degenerate parallelogram. Now, a degenerate parallelogram obviously has to have area 0, so this is the only one that has the appropriate 0 when it's a degenerate parallelogram and is the right area. Okay, so that's just a fact from linear algebra. So we're going to apply that in the context here. So to finish my thing before, where J is the Jacobian of G to be defined later. Okay. So under this fact from linear algebra, now I can talk about the Jacobian. And how does this linear transform in the context of uv equals g of xy, which is the context we were talking about before? The local linear transformation representing this at the point xy is just the first partial derivatives of the variable. So if you move the x coordinate of the input, how much does the y coordinate of the output go? So I'll write it first of all in Leibniz notation, which I think is always easiest. How does the output change with respect to x? How does the output change, the first output coordinate change with respect to y? Okay. And then how does the second output coordinate change with respect to x? How does the second output change with respect to y? Okay, so that's matrix notation. I don't want to assume people are too familiar with matrices, but the matrix notation is just a quick way of saying that linear transformation without saying the x's and y's. So you just put the numbers, the coefficients in a box, A21, A22. So that's the matrix of that linear transformation. So the matrix of the local transformation here is, it makes sense, right? Because A11 is how much does u change as x increases? That's the partial derivative of u with respect to x. So it's exactly what you expect. Then how much does, that should be du dy. Sorry about that. du dy, and then it doesn't matter because the determinant is the same both ways. And then I'll make this dv by dx. Okay, and so another way to write this is that it is g prime of, sorry, I can't use prime because it's a two variable system. So d, I'd have to write it with dg1 dx to g2. Okay, it's just easier to write it that way. Okay, and the Jacobian of, sometimes that's called the Jacobian matrix, but the Jacobian determinant is what we really want, which determines the matrix. Is j is equal to du dx dv dy minus du dy dv dx. Those are partial derivatives. So in a partial derivative, you leave x constant and differentiate with respect to y, or vice versa. Okay? Then the key point is that du dv is equal to the absolute value of j times dx dy. Okay, so I said that at the start of the top page, but I hadn't at that point told you what j was. Now I've told you what j is. Okay. So far so good. Now I want to talk about how the density changes, because that was, after all, the whole point of this. So how does the density transform? And this, we're talking about the joint density of x, y transform under uv is g of x, y. Okay. So how does it transform? The probability is kind of, we're going to ignore the artifacts of it not being an exact parallelogram. They're of a lower order, and it turns out they vanish in the limit. So the probability that x, y lies in the rectangle. I'm imagining a little rectangle here. But let's even call it R. So I'll call that rectangle R, and I'll call our little parallelogram here P. So the probability that x, y lies in R has to be the same as the probability that uv lies in P. Because P, if you ignore the fact that it's not an exact parallelogram, it's pretty much the image of x, y under the transformation. So uv is the image, so those have to be the same. Now on the left-hand side, this is equal to the density of x, y dx dy. Okay? And on the right, this is equal to the density of uv, which we probably assume we know the xy version and not the uv version. uv du dv. Now, that's just sort of an area element in the right-hand side, but we already saw that the correct relation of the area element, du dv to dx dy, is via the Jacobian as an extra factor. So times absolute value of j dx dy. Now, so finally, I want uv in terms of xy. That's f uv. uv is equal to f xy xy times the Jacobian of the inverse. So I could write J inverse for the same Jacobian before. And another way of writing that is uv xy of xy times the Jacobian. I'm going to say it's a different Jacobian, J tilde. Now, unfortunately, I think J tilde may be what the textbook calls J. So there's Jacobians in both directions, from xy to uv. There's also a Jacobian going through uv to xy. So I think with the textbook they do it this time J. But you have to remember that J is the J for the inverse transformation. So where J is the Jacobian determinant of the inverse transformation. Luckily there is an inverse transformation because of all of those assumptions we made. Transformation xy equals G inverse of uv. So, okay, if you want to be really precise about that, you can write J prime is the determinant of the following matrix. I have to do dg inverse by du, uv, dg, that's dg1 inverse du, dg1 inverse by dv, uv. So all of this is easier to do in practice, but if you want a formula, that's what it is. dg1 inverse of du, dv, uv. No, sorry, dg2 inverse du, dg2 inverse dv. Okay, so it's what it has to be. Okay. Now, and so you can calculate it either way. If the g inverse is easier to calculate, you do it that way. And it's also, this is 1 over j. So you can calculate it forwards or backwards. And I now just realize I'm going to have to make a, okay, it's not the inverse function of g1 itself. It's the first component of g inverse. So to avoid confusion, I'm going to have to call that I'm going to have to clear this up. It's the h1. Okay, so where g inverse of uv has two coordinates, h1 uv and h2 uv. So h1 and h2 are the two components of the inverse transformation. You then take those components of the inverse transformation. So I'm going to have to, the h2, the u. Okay, I'll clear this up. The h1 dv and the h2. Sorry about that. Okay, so you can calculate it either way. So let's do an example in the few minutes we have remaining. And this example is actually going to fill in a proof that was left till later on, so that's good. So let's do a great example. And this example will also show you that while it seems like it's only useful for two variable transformations, it's actually useful for finding one variable distributions. So let x and y, so these are the inputs once again, be, x is gamma. I'm going to make it a1 because the scale parameter of a gamma is nuisance. It's just b makes it b times as large as another gamma. So, so I'm just going to make the scale parameter 1. And y is going to be gamma. Okay, let me make that a Greek letter alpha and this one a Greek letter beta. I don't want the beta to be confused for the scale parameter b, but so beta is not a scale parameter, it's a shape parameter. Okay, and these are going to be independent. So this is a theorem that we stated before, and we can give the proof now because we have this general transformations. X plus y is distributed, and I don't think we said the most amazing part of this is the actual independence. Gamma alpha plus beta comma 1, and so let's call that u, and let's call v equal x over x plus y. So how far along is the x out of the sum? That has a beta distribution, alpha comma beta, those are the parameters, and u independent of v. So this is a great theorem. And the best way to, so it seems to be saying things just about individual variables, but actually we can read that off the joint density. So whenever you want a marginal density, you find the joint density first, and then read off the statement. So proof, okay? The proof is going to be a great application of our joint transformations, because whatever that, you notice u and v are a joint transformation of the x's and y's. It's not a linear transformation. This is very non-linear. And even adding the x and y together is a bit tricky too. And we'll be able to find the joint density. So x, y. As you know, it's x to the minus alpha, x to the alpha minus 1 e to the minus x divided by gamma of alpha. That's the density of x. Then we have to multiply the density of y because of the independence. Y to the beta minus 1, e to the minus y, divided by gamma of beta. Then, so that's what it is. I'm going to simplify a little bit. Oh no, I don't need to simplify, but you see I can put the x and y together in that. Now f u v of uv is equal to, well, fxy of xy. So u and v and xy are related by that transformation there, times absolute value of j tilde. Or, if you wanted to do the forwards version, that would, you could also do the inverse Jacobian. But here, this is the backwards Jacobian. That's actually an easier one to do, because